Hi, I'm Ciro Martinez, and this is my AP problem number 7. Under standard conditions at 25 degrees Celsius, zinc solid reacts with cobalt 2 plus aqueous to produce cobalt solid. So we have to use a standard reduction table to figure this problem out. Write the balanced half oxidation reaction equation. So the balanced oxidation reaction is Zn solid produces Zn2 plus 2E minus. We know this the oxidation reaction because Zn starts off with a +0 charge and ends up with a +2 charge. So for Roman numeral 2, we have to write the balanced net ionic equation for the overall reaction. The balanced net ionic equation is Zn solid plus CO2 plus aqueous produces Zn2 plus aqueous plus CO solid. That's the balanced net ionic equation because the 2 electrons should have crossed out after we flipped the zinc half oxidation reaction around. For Roman numeral number 3, we have to calculate the standard potential for the overall reaction at 25 degrees Celsius. So we take both half reactions and we find the voltage for them using a standard reduction table, and we add together the voltages, so we get 0.76 minus 0.28 equals 0.48. So the standard potential is 0.48 volts. So for B, at 25 degrees Celsius, H2O2 decomposes according to the following reaction. 2H2O2 aqueous produces 2H2O liquid plus O2 gas. The standard potential is 0.55 volts. For I, we have to determine the value of the standard free enthalpy change, delta G, for the reaction at 25 degrees Celsius. So we're going to use the equation delta G equals negative NFE. So we plug in 2 for that's how many electrons were used in the reaction. Then we plug in 96,485 because it's the constant, and we plug in 0.55 because it's the constant E. So we get delta G equals negative 110,000 joules, or negative 110 kilojoules. For B, Roman numeral 2, we have to determine the value of the equilibrium constant for the reaction at 25 degrees Celsius. So we take this equation, E to the power of negative delta G over RT equals K. So K is equal to E to the power of negative 110,000 over 8.31 times 298. So we get K is equal to E to the 44.4th power, so K is equal to 1.9 times 10 to the 19th power. For Roman numeral 3b, the standard reduction potential for the half reaction O2 gas plus 4H plus aqueous plus 4E minus produces 2H2O liquid has a value of 1.23 volts. Using this information in addition to the information given above, determine the value of the standard reduction potential of the half reaction below. O2 gas plus 2H plus aqueous plus 2E minus produces H2O2. For Roman numeral 3b, we have to take this equation, and we have to set them equal to each other to try to get this equation. So we have to flip the reaction H2O2 aqueous produces 2O2 gas plus 2H plus aqueous plus 2 electrons, and we also have to double it and set it equal to O2 gas plus 4H plus aqueous plus 4E minus produces 2H2O liquid. So after we set them equal to each other and we multiply by the second reaction by 2, we get 2H2O2 aqueous produces 2H2O liquid plus O2, and the volts is going to be 1.23 volts minus X volts equals 0.55 volts. So we take this and we put it over here, so it's 1.23 volts minus X volts equals 0.55 volts, and we subtract by 1.23 volts and then we divide by negative 1, so we get X is equal to 0.68 volts. So the standard E cell is equal to 0.68 volts. C. In an electrolytic cell, Cu solid is produced by the electrolysis of CuSO4 aqueous. Calculate the maximum mass of the Cu solid that can be deposited by a direct current of 100 amperes passed through 5.0 liters of 2.0 molarity CuSO4 aqueous for a period of 1 hour. Take 1 hour and we multiply it by 60 minutes and we multiply it by 60 seconds. And then we divide it by 96,485 columns. Then we divide it by 2 moles of electrons. Then we multiply it by 100 amps and we multiply it again by its molar mass of 63.55 grams of Cu, and we get 119 grams of Cu.